In the previous week, we started to talk about the detecting noise from the original signal. So we saw that in the block diagram of data transmission, this block diagram start from source. This source produce the data. We encode or encrypt the data, and via a channel, this channel can be wire or wireless, we send the data to the processor, and at the output of the processor we will have a random data contain information. Now in the detector, first of all, we need to find the value of V, or in another word, we need to find the output of the processor, the V signal. After that, according to the value of V, we need to extract the noise. We need to detect the original signal from the noise. So at the output of the detector, we will have the received signal or received data that will transmit to the destination. Now we reach up to here that we investigate the match processor, and we wanted to calculate the output of the matched processor. One kind of linear processor. Matched processor is a one kind of linear processor. So in the previous week, we investigated the special case. What was the special case? We said that we suppose that we don't have noise. We investigate the noiseless case. In the noiseless case, we found that if we calculate the output of matched processor, we will find the energy of the signal. The energy of the signal. So then we define the signal to noise ratio. Now I want to find the output of matched processor in the presence of noise. Okay? Let's calculate the output of V. Now we can examine the output of the match processor when noise is present. When noise is present. So we learned that when noise is present, we have two cases of signal, or two cases of signal can occur. Look at here. Generally, I defined Xi like that. I said that Xi is equal to Si plus Ni. So we said that we can write Si, or we can divide Si as S0i and S1i. If dt is 0 and if dt is 1. And also Si S0I can represent by minus Si, and S1I can represent by Si. Now, according to this case, I can write that Xi can be written like S1I plus Ni and S0I plus Ni. Now let's investigate the case 1. In the case 1, I want to find the output of matched processor. What was the formula? The formula was that V is equal to summation of Si, Xi when I changed from 0 up to Nx minus 1. Now, easily I can substitute this phrase instead of Xi. I can write Si times S1I plus Ni is equal to I0 Nx minus 1 Si. Now, I said that instead of S1I, I can write Si plus Ni. So this phrase will equal to Si square plus Si Ni. I is equal to 0, Nx minus 1. I is equal to 0, Nx minus 1. Now, look at here. What is this? What is this phrase?
Energy.
Energy.
Yes. Energy of signal. And this is can also called as N star I. Or we can only write N star. N star is also a noisy signal, a noise signal. What does it mean? It means that if I have 1 at the output of source, in the output of processor, I will have energy of signal plus N star. And N star can define as Si Ni. Can define as Si Ni. So let's investigate the second case. In the second case, we have Xi is equal to S0I plus Ni. So again, if I write the output of matched processor, I can find that I will have S0I plus Ni. Again, if I write minus Si instead of S01, I can find that. If you look at here, you can find that Si square plus Sin I. Now again, this is my energy of signal, and I can write that minus energy of signal plus N star. Here I will have the minus of energy. So briefly, we can say that the output of signal, the output of matched processor will be equal to S star plus N star. And my S star will be equal to energy of signal when I have S1I, and S star will be equal to minus energy of signal when I have SE0. Now look at here what happened. From here, we can find that normally most of the V that occurred in 1 will have positive value, and in the case of 0 will have negative value. What does it mean? It means that I can define a threshold tau is equal to 0 in the detector, in the detector block. So the input of detector is V. Here I want to calculate DR. I define a threshold which is equal to 0, and I say that if V is greater or equal than 0, my DR is 1, and if V is less than 0, my DR is equal to 0. It doesn't matter the value of V here. It doesn't matter the value of here is 5, 6, 18, 24, or etc. All of these numbers accepted as 1. And again here, it doesn't matter I have minus 16, minus 19, minus 20, minus 100, it doesn't matter. All of them accepted as 0. If energy of signal is positive, all of the signals accepted as 1. If my signal, my V is negative, all of them accepted as 0. With defining a threshold in detector like that, I can detect the DR as 1 and 0. Using this process, I can transmit the data correctly. If you look at here, you can find that using this process and this method, if dt is 0, it means that if my source produce 0, using this process, I will have 0 at the destination. And if I have 1, regardless of the value of ni, I will have also 1. And here I have written all of the things that I have talked about that, and you can read and learn. Now, I said that the V signal is a random signal. And because the noise is in the form of Gaussian distribution, my V, my random signal V, or in other words, the shape of the V is also in the form of Gaussian distribution. In the Gauss distribution, in the Gaussian distribution, we know that each distribution has mean and variance or standard deviation. It means that our V signal also will have mean value and variance. How can I calculate? How can I find the value of mean of signal V? We say that the mean of signal V is equal to energy of signal when my xi is like that, and is equal to minus energy of signal when xi is like that. It means that the value of energy of the signal plays an important role in the case of detecting noise from the original signal. Now, how can I calculate the variance of the signal? I can say that the variance of the signal is equal to variance of the noisy signal times the energy. Actually, it comes from we need to multiply the S to the signal N in the standard deviation, because I calculate the square of a standard deviation, which means that variance. This formula can be calculated. Now, the energy of the signal times the variance of the noisy signal will be the variance of the V signal. Look at here. We can find an interesting result. This is the Gaussian distribution of V when source produce 0, and this is the Gaussian distribution of V when source produce 1. And this 0 is threshold. Look at here, V is noisy, and this V is also noisy. But because, look at here, because energy of signal is bigger than the standard deviation of signal, this section is a standard deviation. Using 0 for threshold, I can detect the 0 and 1. I define a threshold, and here the threshold is 0, and I say that if V is greater than 0, my output is 1, is less than 0, it means that my output is 0. Now, look at here, if energy of signal approximately is equal to the standard deviation, what happened in this case? In this case, I will have error. This section is my error. This section is my also error. Maybe I will have error if the energy of signal is approximately equal to the standard deviation of signal. It means that we will try to have the system with the high energy, or with the less or a small standard deviation. In otherwise, we will have error. And there are some methods to reduce this error and detect the error also. But here we don't talk about this section. We suppose that the energy of the signal is greater than a standard deviation of signal. Look at here, this is an example. At this example, guys, everyone can hear me?
Yes, teacher.
Yes, teacher.
Yes,
Okay. Okay. We produce the signal, actually source produce 200 data signal, 110, 100 minus 10. So we suppose that minus 10 is S0 and 10 as S1. So the energy of the signal is 100. We suppose that the Gaussian noise is added to our signal. The Gaussian noise with the standard deviation of 1. With the standard deviation of 1. Now, if my standard deviation is 1, first of all, I have to calculate the SNR, signal to noise ratio. Signal to noise ratio says that energy of the signal divided by the variance of the noise. Because the standard deviation is 1, the variance will be 1. 0 divided by 1 is equal to 0. In the decibel unit is 20 decibel. The logarithm form of this 100 can be represented as decibel. 10 to the power of 2, log of 10 to the power of 2, 2 comes here, 2 will multiply by 10, which is equal to 20, and log 10 of 10 is equal to 1. Now, we said that 100 of signals is 10. Get here? 10. And this 10 accepted as 1, S1. Instead of S1, we can write 10. It means that I will have V is equal to 10x. 10x. Now, if I define x as S0 plus n, at these S0, instead of S0, I write minus 10. And if I substitute to the formula, I can find that minus n plus 10, n, and if x is S1 plus n, I will have energy of the signal plus 10 n. Now, we said that. Now, I have two signal, minus energy of signal plus 10 n and plus energy of signal plus 10 n. If I draw, look at here. If I draw the energy of S and minus energy of S, I can find that if I define 0 as threshold, I can detect my 0 and 1 with together, regardless of the value of noise. Look at here. How could I detect the signal? I said that here because the energy of signal is greater than the standard deviation of signal. If this case happens, it means that my SNR, signal to noise ratio, is high. If sigma of n is equal to 10, look at here what happens. Here, if I calculate the SNR, I can find that the value of SNR will be 1. And in the decibel form is 0 decibel. Again, if I write the value of V and calculate the value of V, I can find that I will have error at the 0. It means that I cannot correctly detect my signal's value from the noise. I cannot extract my original signal from the noise. SNR is equal to 1, and an error occurs. SNR is 100. I don't have error. What does it mean? It means that the SNR is an important factor that determines the reliability of data transmission system in terms of its probability of error. So we can reduce the number of errors by increasing the signal to noise ratio. If I increase the ratio of signal to noise, I can reduce the probability of error, or the SNR also can be improved by increasing the signal of energy or reducing the variance of noise.